afternoon and welcome to this trial session. In this trial session, I'll be covering a topic which is covered at A-levels, namely differential equations. What are differential equations? A basic introduction to differential equations and how to solve a simple model in differential equations. So very briefly, differential equations are essentially a way to model real-life phenomena. What does that mean? That means if I want to model, let's say, the which we had before, let's say, which was COVID-19, people used differential equations to model that, to see the expected recovery rates, to see the expected death rates, and life expectancies, and so on. And also that differential equations can be used in measuring the oxygen consumption from a plant, right? We can use differential equations to describe that phenomena. So ultimately, these are just examples of what differential equations are used for. So they are very important, and I believe that if they're well studied at A levels, they can really help, especially if you're planning to take on a mathematically heavy course for university, such as engineering or mathematics itself. Okay, so very briefly, differential equations. So if I have, for example, if I say the population, right? If I want to model a population dynamic, let's say I want to model the population in the UK, the United Kingdom, how would I do so? I would firstly assign variables. What does variable mean? Variable means things which vary. So for example, population I can denote by P, where P is a function of time. So as you can see, P is a variable. It changes, it varies with time, okay? But T is time. Okay, now you've covered something at AS level, and if you haven't, obviously, you can reach out, but there is something which is called, which we learned in differentiation, that, for example, dp by dt, this notation, it's called the Leibniz notation, and it's different from the following notation. This essentially means the same thing. Okay, these are two notations, and sometimes you might find this inside textbooks, but this is a notation which we are not going to cover at this course. We are mainly going to focus on this notation. But to emphasize that these two are the same, one is the Newtonian notation, and the other, which we are going to work through, is called the Leibniz notation. And I believe the Leibniz notation is more useful in differential equation because we can explicitly see what our variables depend on and what they vary with. Okay, so dp by dt. My first question actually is how to read equation. Okay, so how do we read dp by dt? The way to read it is the following. I would say, how does the population change with time? Okay, so remember the D represents change. So how is the population changing with time? With time meaning the denominator has time over here. So that's the question you ask yourself. Let me repeat myself once again. How does the population change with time? So that's the question many mathematical modelers ask themselves, and then they come up with observations and something which they can put together to relate this rate of change. Another way to read it is the rate of change of population. Okay, so if I assume, right, that the rate of change of population, right, is proportional to the population, what does that mean? So let me write that down and then we can discuss what that means. So it's proportional to the population. Okay, so where k is a proportionality constant, k is a constant. So k is not a variable because it doesn't change with time, it doesn't change with anything. It's rather something which is constant throughout our entire observation. So what this equation over here means is that if I change, or if I double the population over here, right? If I replace this and if I double the population, what happens to the rate? It also doubles, okay? This would also double. If I decrease the population, the rate of change of the population, or how the population changes with time, would also decrease. That's all it means, okay? So it essentially means that the rate of change of population increases or decreases with the population. It's a very basic assumption, and this assumption allows us to form our first encounterment of our first differential equation, which is the following, which is in the box. Okay, let me highlight this because it's our first differential equation. Okay, all right, brilliant. Okay, so what do we do after we have something which looks like this, a differential equation? We need to learn how to solve this. Okay, because at the end, what we want is something on the lines of p is equal to such and such, right? Where we find the function p, p of t, right? We want to find that function, so we see if I input certain values, how is the population changing? I can essentially see the population dynamics, which was my goal, as I stated. So how to solve this? So if I write the equation down, dp dt is equal to k of p, the first thing we need to do is we need to separate the variables. We need to group terms which are similar, right? For example, dp has a p, which is a variable, and p is on the right hand side in our equation, right? So it's actually over here. So what I want to do is I want to separate the variables. So I want to reorganize my equation. So I get p there, I can get the dt here, and it looks different. So what we do is this is called the separation of variables. Let me write that down. It's actually important. Separation of variables. So to do this, we would let's say I multiply through by dt. So if I have dt, dp over dt, I'm multiplying through by dt, and we have kp times by dt. So if I multiply through by dt, right, this cancels out, and I'm left with dp is equal to kp dt. The next question is to separate the p and get it to the other side, right? Because p matches that term there, and we want to, obviously, as I said, separate the variables, group the terms, the variables which are alike on one side. So how would I get the p on the other side? I would have to divide by p. So I would have to divide by p. That would be dp over p is equal to kp dt over p. So I can cancel these p's out, and I'm left with dp over p is equal to k dt. Okay, so now we're in a very good position. So once you have an equation in this form, okay, if you have an equation in this form, it's good because now you can start solving this equation. And the way you solve it is you do something which is actually the opposite of differentiation. Note that this is actually, these are differential operators, or differential quantities which we get from the Leibniz notation. So it's very worth knowing that we're going to use something which is the opposite of differential equation, right? So it's the opposite, and it's called integration. Okay? It's the opposite of differentiation. Okay, so if I now take the integral on both sides, what would happen? So this would imply that dp over p, how can I take the integral of that, and how can I take the integral of k with respect to dt? So remember that dp over p, excuse me, can be written as 1 over p times by dp. Okay, so just very quickly, this can be written as 1 over p times dp. And we know that 1 over p, what's the integral of 1 over p? It's equal to the ln of p, correct? The natural logarithm. So we have the ln of p is equal to, now what is the differential of a constant? Is simply that constant times by the variable kt plus a constant of integration c. C is a constant of integration. Okay, very good, but note we have a very good equation, but this equation is still not in terms of p, because we essentially want the function pt in terms of something, okay? So how can I make p the subject? Now you may recall from your studies in logarithms and in exponential functions that this is essentially, we can take the exponential on both sides, and we can write it like the following: kt plus c. Okay, so note that the natural logarithm and the exponential function cancel out, and we have p is equal to e to the kt plus c. Now, e to the c, I can rewrite this as, just to clear it out, I can write it as e to the kt multiplied by e to the c using the laws of indices, and I can say, well, e to the c is just a constant. Remember that e is 2.17 something, and a is equal to e to the c. Therefore, I can rewrite this entire expression as p is equal to a, where a is a constant, as defined earlier, times by e to the kt. So very good. I mean, this is essentially the solution. And now, if I'm given a time, I'm given, I'm given the variables or the quantities, and initial conditions, I can find the dynamics of the population and how it changes with time. Thank you very much, and thank you for listening.